Another epoch of studying exoplanet demographics. Exoplanets as populations. And what we learned from Kepler is that the diversity of planets in our galaxy far exceeds the diversity of planets in our own solar system. And now, 25 years later, after that first discovery, we are literally knocking on the door of a new epoch of exploration, which is the study of exoplanet atmospheres. And it's going to give us a new lens on their diversity.
When you think about Earth's atmosphere, it's this thin little layer that is hovering right above the Earth's crust. If you try to imagine measuring properties of an atmosphere at the distances that we're talking about, it seems mind-bogglingly difficult. How do you go about gaining insight into something that's so thin at such an enormous distance?
Yeah. You asked John earlier, what is the power of Webb, over Hubble? Besides the fact that we have 10 times the collecting area, so we get more photons, that allows us to increase the precision of our measurements so we can see very tiny features of these, from these very small exoplanets. But also, Webb is a spectroscopic machine. We're going to be looking in color space. Hubble produced these very famous images that we all know and love, and Webb will produce amazing images of the cosmos as well. But what we're also going to be doing with Webb is collecting light from astrophysical objects like exoplanets, spreading that light out into a rainbow and looking at that rainbow with very close scrutiny. And that will allow us to see the chemical fingerprints that an atmosphere leaves on the light. For exoplanets with Webb, what we're going to do, we're going to observe them in many different ways. But one of the primary ways is to observe the star when the planet is transiting across the surface. And when that happens, this very thin layer of the atmosphere will intercept some of the photons from the star on its way to our telescope. And then we will spread that light out into a rainbow and disentangle these chemical fingerprints from the atmosphere from the chemical fingerprints of the host star, for example.
So do you have any sense right now of what fraction of exoplanets have a significant atmosphere?
That's a great question. And I would have to say for the Earth-like planets, we don't yet know. We've done this game a little bit with Hubble. We have observed about a couple dozen of what we call hot Jupiters, maybe down to a hot Neptune-sized planet. We've looked at them atmospherically, at their atmospheric signatures with Hubble, and with a very narrow slice of this color space that captures water features, for example, from the water molecule. Giant planets like Jupiter have very thick hydrogen-rich envelopes. In terms of an atmosphere, a large percentage of the mass of Jupiter, for example, is due to this envelope, or what planetary scientists would call an atmosphere. When you go down to the terrestrial-sized planets, especially when they're orbiting very close to their host star, we think that those atmospheres get stripped away relatively easily. And so we want to know what fraction have atmospheres, because that's going to have significant implications for whether or not they are potential abodes of life. And so that is exactly one of the things that we want to learn, is what fraction of terrestrial-sized planets actually have atmospheres.
When you look at an atmosphere of, say, a terrestrial-sized planet, presumably finding something that has a composition not unlike Earth, that presumably that's the home run. But are there other markers within an atmosphere that you will be looking for? And if you see them, you can say there is some case to be made that a living system may be responsible for those markers.
Well, Webb was not designed to be a life finder. And we have a lot to learn before we start looking in earnest for biosignatures, these signatures of life imparted by life that has actually taken a global toehold of a planet and influenced the atmosphere in a global way that's remotely detectable. I mentioned that Kepler uncovered this diversity of planets. One of the things right out the gate that Kepler discovered is that the most common type of planet in the galaxy orbiting in the inner solar systems is a type of planet we don't even have in our solar system. In our solar system, we've got the tiny rocky things orbiting nearby. We've got the big giants orbiting far away. But in the galaxy, it turns out that the most common type of planet is something in between. And we don't know what its nature is. It's been suggested that a large fraction of these planets started out as something like Neptune, but in the dynamical formation and evolution processes of planetary systems, those planets could have migrated inwards towards their host star. So what happens if you take a Neptune and you plunk it down in an orbit like Earth's? What's going to happen to it? Well, scientists say that what happens to it is the hydrogen envelope gets completely stripped away, leaving a rocky core. So rocky cores are great for life, right? Is that a potential abode of life? Does that broaden the number of landscapes available for life in the galaxy? We don't know. So we want to understand that mysterious population that we don't have in our own solar system. And in doing so, by looking at the atmospheres, we will have diagnostics that allow us to understand all of the physical processes that sculpt a planetary atmosphere and leave something after 1 billion or 2 billion years where life could or could not take a toehold.
So that most common of all planets revealed by those surveys, can you give us a sense of what those planets are like? I mean, how big are they? If they're bigger than us, but not as big as, say, Jupiter, where do they fit in the range?
Our terrestrial planets, let's do it in terms of Earth units. Let's call Earth 1. So Earth, Venus are about 1 Earth radius. Mars is about half that. Mercury is about the size of our moon, a little bit bigger. The next largest thing in our solar system is Neptune and Uranus at 4 times the size of the Earth. Jupiter, 10 times the size of the Earth. So in this range between 1 and 4, we don't really have anything in our solar system unless you want to keep looking out at the Kuiper Belt and the very distant regions of the solar system. Maybe there's something still lurking there that's yet to be discovered. But as far as we know today, there's nothing in this range of 1 to 4. And the most common type of planet that we know of is in the size range of like 1.5 to 2.5 Earth radii.
Am I right that, is your daughter a lead scientist on a mission to explore those kinds of planets? Is that correct?
Yes, she is. She's the principal investigator of one of the largest programs that was selected for Cycle 1 that will observe about a dozen planets in that size range in order to better understand their diversity and how they transform themselves from something more like Neptune that has a hydrogen envelope, which we call a primordial atmosphere, by the way, because it's formed, we think, during the planet formation process, versus the atmosphere of Earth, in comparison with the atmosphere of Earth, which we believe was mostly outgassed. We call it a secondary atmosphere because it was outgassed later in the Earth's evolution. And so, yes, my daughter is a research astronomer at NASA Ames Research Center, and she is the PI of that mission, and I'm actually a co-investigator on it as well.
Well, that's great. So, Adam, let's turn to one of the main science projects that the Webb will be focused upon, which is in the arena of early universe cosmology. And it's interesting because what I'd like to discuss for a few minutes is something that was not on the scientific radar when the Webb was being built. It's this issue called the Hubble tension, having to do with measurements in the last few years that have really begun to show potential discrepancy in our observations of cosmological qualities of the world and our theoretical understanding of cosmology. It has to do with the expansion of space. I'll let you explain it to us, but I'll simply note that over the years, the rate of expansion of space has been this vital quantity that we have been trying to nail down. So can you give us a sense of where we stand on understanding the expansion rate of the universe, the tension that we're now under, and what Webb might do to help resolve it?
Sure. So in the last 20 years, we've developed a new model of cosmology, and we think we understand the universe and can therefore make predictions. And one of the key predictions is to observe the universe shortly after the Big Bang with the cosmic microwave background and essentially calibrate the state of the universe then, how fast it was expanding, what it was composed of, and then use our understanding of the physics of the universe to really predict or extrapolate to the present time, how fast should the universe be expanding now? And then we measure the expansion rate, a number called the Hubble constant. And the Hubble Space Telescope was designed largely to measure the Hubble constant to about 10% precision. And that was successful. And maybe we should have quit while we were ahead, because we continued to measure better with the newer instruments in Hubble. And as we approached percent level precision, which is about where we are now, we've begun to see, I guess, sort of cracks in this sort of standard model. Our ability to go from end to end of the universe and explain the dynamics of the expanding universe is falling short. There's a discrepancy now, and it's becoming quite significant. And so Hubble has left us with this kind of cliffhanger, if you will. And we hope that the James Webb Space Telescope can step in and sort of help us resolve or better understand what's going on.
So in terms of the actual numbers, for those in the audience who like the details, what is the best observational number that we have for the expansion rate, and what would we have anticipated based on the theory?
Right. So before Hubble launched, it was somewhere between 50 and 100, the universe somewhere between 10 and 20 billion years old. And then after these observations and careful measurements, we're now down to a range of 67 to 73, which sounds like a lot of progress. You know, the glass is half full here. We understand a great deal about the universe. The problem is the cosmic microwave background data says it should be 67 plus or minus 0.5. And the local measurements generally coalesce around 73 plus or minus 1.5 or so. And so this has become uncomfortably far apart and suggests maybe there's another wrinkle in the standard model of the universe. Maybe these concepts or these realities like dark energy and dark matter are a little more complicated, a little less vanilla, have some other important physics that we're not including in our description of the universe.
So just quickly, when you say 67 or 73, can you just give a sense of what those numbers are telling us about the expansion of space?
So they're in funny units that we call kilometers per second per megaparsec. So they say every time you go out another megaparsec, which is like 3 million light years, the universe is expanding 67 to 73 kilometers per second faster. But you could think of that number as a doubling rate. So at that expansion rate, it means, the universe will double about every 10 billion years at this point.
Got it. So John, certainly over the course of my career in physics, I don't work on observations and the cosmological parameters are more of an input to me as opposed to something that I've spent any time ever trying to determine. But I've witnessed a tension between different groups claiming different values for the expansion of space over a long period of time. Do you consider this tension to be different from what we have heard in the past, or do you anticipate somehow it'll all just work out and the standard cosmological theory will still work at the end of the Webb observations?
Good question. So when I started in on this world of cosmology, there really wasn't much of a number. When Adam says 50 or 100, it's like we don't know. And so at that time, the disputes between those groups were extremely vigorous, and people were quite sure they were right. And now we know neither group was quite right. So I'm an experimenter. I like to measure things, and I'm always afraid that it's my fault when I get an answer that somebody doesn't agree with. So that's my guess, of course, that we're making some error in our measurement and nature has just fooled us about something. But that makes us a little bit blind to the possibility that maybe nature has really got something to tell us, that there's something that not in our story that we might just be happening on, and we have to be really, really careful. So my expectation this time is why wouldn't it be complicated? Nature is always complicated. So I would not be surprised a bit if we are happening on something really remarkable.
And if I could just jump in here for 1 second, I will say what's really interesting about the current moment is in the past, when, as John said, people disagreed about the value of this number, they thought they were measuring the same thing. They were measuring it locally. They were using the same tools. So we knew both things couldn't be right. What's so fascinating about this is we're actually measuring this quantity starting at opposite ends of the universe. And so in this case, it's possible that both measurements are right, and it's telling us something about the story we use to connect the two. And so while I can't tell you yet what the answer is, that makes it, I think, a much more interesting moment because it has the potential to give us a clue about the universe as opposed to just who's right?
Right. Now, it would be asking too much for you to, as you say, tell us what the ultimate answer will be. But there are some potential stories on the table. Do any of them strike you as plausible at the moment, or are they all just sort of cooked up to try to make things work?
Right. I'm in a funny position to tell you what's plausible because, 20 years ago, when we saw the universe was accelerating, it was attributed to dark energy and a cosmological constant. And as you know, there's about 120 orders of magnitude gap between a sort of quantum level understanding of the cosmological constant and what we actually see. So is that plausible? Are we comfortable with that explanation? So in that context, some of the things that are suggested now are, another episode of dark energy before the universe became transparent, dark matter decaying over time, another relativistic particle like a neutrino. Believe it or not, any of these things can explain why the universe is not tracking the simplest cosmological model. And so as an observer, I struggle with what's natural, what's surprising. The universe is so surprising to me that, I find I don't have a good